And today is day 3 of our Verilog Project Series. And today we will going to implement our Johnson counter. Like in past 2 video, I have discussed the implementation of RAM. I have also discussed its RTL design along with its verification. And in second video, I have discussed about the 4-bit counter. So today we will discuss about the Johnson counter. So first of all, we discuss the theory of Johnson counter and then we will start our implementation part. So here it is given like that on the rising edge of clock. So whenever you get rising edge of clock, like suppose here it is your clock. So at every rising edge of your clock, if your reset signal is high, let's say this is your reset signal. So if your reset signal is high, so your count value should be 0. Like here your count value should be 0 only. Okay, whenever your reset is high. And like here it is 0, and whenever your reset is low, like whenever your reset goes low, then you can increment your count. And so in Johnson counter, if you have 4-bit number, so total number of possible state is 2. So total you have 8 state. So first of all, it will goes from 0 to 1, like it will moves from 0 to 1, and then it will goes to 3, and then it will go, and then it will move to 7 and so on. So this is how our Johnson counter will look like. So first of all, we will try to implement its RTL code and then we will start implementing its verification code. Okay, so let's start the implementation of RTL code. So let me take you to the screen. So here I have mentioned the question which we have to achieve. So here you can see we have one clock. So first of all, let's declare a module. So first of all, let's declare the module. So module, name of module was Johnson counter. So Johnson counter. And let's declare all the signals. So clock, reset and count signal. Okay, so this was the signal. Now let's declare its port. So input, wire, clock and our reset was the input signal, and count was an output signal. And since we have 4-bit, to total 4-bit count signal we have to consider. So output, and it should be a res type, and 3 down 0 means 4-bit, and count. Okay, so this is how we can declare our ports for Johnson counter. Now let's start the logic implementation. So see, we have to consider the rising edge of clock. So that means always @ pause edge of clock. Whenever your pause edge of clock will arise, so first of all you have to check condition of reset. So if reset is high, your count value should be 0. Okay, so 40 has 0. Okay, so whenever your reset is active high, so you can make your count value to 0. And for low, let's note down the logic. So if your reset signal is low, so let's begin. And so see, here you can implement it in many ways, but we have to consider case only whenever such situation arises. So it will be easy for us to implement this by using case. So I am considering one case count. Okay, so let's say whenever our value was 4 tick B 0 0 0, then after that, so whenever your count value is 0, so it will, your count value is moves to 0 0 0 1. Okay, so this is how you can consider, like whenever you have count value of 0, so your count value will moves to 0 0 0 1. Now so see, here I have listed down all the cases. Now here, as we have started the case, so we can put AND case. Okay, so this is how we can implement our Johnson counter. Now let's consider AND module here. AND module. So we have implemented our RTL part. Now let's start the verification part. So let's consider one module TB. Okay, we have considered the one module TB, AND module. Now let's list down the signals. So res type of clock and reset, and wire type of 4-bit value of 4-bit value of count. Okay, so this is how we can note it down. And now let's connect our RTL to our test bench. So first of all, let's consider this only from here. So we have considered this, and let's write it here DUT. Now see, first of all we have to generate a clock. So for that we are considering one initial begin block, and in that block we are initializing our clock to 0, and then to generate our clock we are considering one forever loop. So forever hashtag 5. So we are considering 5 unit of time delay. So hashtag 5 clock is equal to negative of clock. So this is how you can generate your clock. Now let's consider the logic. So to write the logic, we can consider task. So whenever your reset task was called, so your automatically logic was implemented. So we are considering one task reset. Okay. So we have considered one reset task. So in reset task, initially your reset should be high. So we are considering high. So whenever your reset is high, your count value should be 0. Okay. And after some time unit, let's say 20 or let's say 10. After 10 units of time delay, you are making your reset low. Okay. So you are making your reset low. That means your count has been implementing. So you have make your count low. So you have made your reset low. That means your count has been increasing as per our requirement. Okay. So this is how you can implement your task. Now let's consider one initial block. So initial, begin and end. So we have considered one initial block, and then we are calling our reset task. So whenever you are calling your reset task, so for the first 10 cycle, it will be high. Okay. So your reset value is high for first 10 cycle, and that means your count value is 0. Okay. I hope you understand. Whenever your reset is high, that means your count value is 0. And after that 10 unit of time delay, you are making your reset signal should be low. So that means your count should be incrementing by something like whatever sequence we have decided. Okay. So we have call our reset task, and after 70 unit of time delay, we are calling again reset task. What does it mean? See, it means like first of all, we have included reset task. That means your first unit of time delay. That means like 10 unit of time delay, your reset is high and then low. And after 70 unit of time delay, you can again making your reset should be high. So again, you are making your reset signal is high. So that means your count value is roll up to 0. Okay. So this is how you can implement your verification plan. Now let's consider a dump file. So since we are doing in PDA, so it is required to include dump file to check the waveform. So initial begin and $dump file. So you can also practice this in EDA. And if you want separate session on how to use EDA, so let me know. I will make this. So I think almost we have covered now. So let's after some unit of time delay, like 50 unit of time delay, we are calling $finish. That means your simulation should be terminated. Okay. So we have called the $finish after 50 unit of time delay. Now let's start our simulation. So I am running our code. Let's see whether we are getting some error or it will be working fine. So see, let's check the waveform. So here you can see that whenever your clock goes high, here your reset signal is high. That means your count value is 0. And in next clock edge, so here your reset is low and your count is incrementing. So see, here your count is incrementing 1 and then 3 and then 7 and then F and then E and then C and then 8 and then again it is rolling up to 0. Okay. So now here you can see your reset is high. So here you have made your reset high. So at the next process of clock, it is rolling up to 0. And then again it will start incrementing after reset is low. So this is how you can check your waveform. Okay. So I hope it is clear to you. And still if you have any doubt, so you can connect with me and also write down your doubt in comment section. We will try to answer this. Okay. So thanks for watching.